So in this lesson, we're going to discuss when a function is or is not differentiable. When we use the word differentiable, that means that we're able to evaluate the derivative. And here we have three examples of graphs. And the question is, can you, just by looking at these graphs, identify where the functions are not differentiable? And if so, explain why. Well, part of the hint here is we're looking at this value a, and that a lines up with this point here. And that point is known as a cusp. But the question is, why is that point not differentiable? So we're going to explore that. If we look at the second example, we see that A lines up with a discontinuity. There's a jump discontinuity. So that should be an obvious case why it's not differentiable. And in the last one, we have a vertical tangent line. And then we'll explain why that case is not differentiable. So let's look at these one at a time. And with this first one, I'm going to pull up a GeoGebra graph. And the GeoGebra graph lets me look at the slope of the tangent line. And as I move this tangent line closer and closer to the cusp, we see that on the right-hand side, I have a slope of positive 2. I'm sorry, that was the left-hand side. We have a slope of positive 2. But now when we approach this from the right-hand side, we are approaching a slope of negative 2. So the left-hand side slope is positive 2. The right-hand side slope is negative 2. The left slope is not equal to the right slope, which is why the tangent line is not defined at that point. This brings us back to how we first developed the equation for the tangent line, how we first defined the derivative, and that was using limits. And if the left limit does not match the right limit, then we say it is dNE. So the tangent line does not exist at that point. That means the derivative is not defined at that point. If we come to this next example, we see that the function is not continuous at that point. So differentiability is going to require continuity. So the function must be continuous at a point. Be differentiable. With that said, continuity alone is not enough for differentiability. And in a college math course, we would say continuity is necessary, but not sufficient. Here, continuity is necessary, but it's not sufficient for differentiability. We need the tangent slope to be equal from the left and the right side, which is how derivatives are defined. And then in this next example, I'll pull up a GeoGebra graph again. And we see that if I take the tangent slope as we go towards 0 from the left, we see we're approaching numbers smaller and smaller as I get closer and closer to 0. Well, that's the x value. We see that the slope values are getting larger and larger. I'm at slope equals 8, 9, 10, 11, 13, 20, 30. It's going up to a very large number, and eventually the tangent line slope is gone. It's not defined anymore. And that's because the slope of a vertical line is undefined. So if the slope of a vertical line is undefined, then so is the tangent at that location. And since the derivative is used to calculate slope, that means that this function is not differentiable where there's a vertical tangent line. So, with that said, we'll summarize the requirements for differentiability. 1, in order for a function to be differentiable at a point, it must be continuous at that point. 2, however, continuity alone is not enough. In addition, the tangent line must be defined at the point. And we have our cases here, a cusp, a corner. These will have different slopes on the left and right hand side. A vertical tangent line will have an undefined slope, so the derivative does not exist. And of course, there is condition 1, if it's not continuous, we could find that it cannot be continuous with a jump discontinuity, a vertical asymptote, a point or hole, and these would be cases where it's not differentiable at the point. All right, that's the end of the lesson. You can go to your worksheets now and identify where functions are not differentiable.